Let's say that we have an isolated system, so there is no energy exchange with the environment, and this is at equilibrium. So from our previous discussion, this means that there is a number of accessible states. So I will call this omega is the number of accessible states. And what are those states again? Out of all possible states of the system, these are the ones that satisfies the restriction that is imposed on the system. For example, the system is isolated, so it must have a fixed total energy. So what are the states that give us that fixed total energy? And because I have equilibrium, due to our postulate of equal a priori probabilities, the probability of each accessible state is the same. So each accessible state has equal probability. And what is that probability? Because I have a total of omega accessible states, it is equal to 1 over omega. And this probability P is not a function of time. It is time independent probability because the system has reached equilibrium. So now I'm interested in a parameter that describes the system. So there is a parameter y that describes the system. This could be, for example, the total magnetic moment m, example, total magnetic moment capital M. It could be the pressure P, etc. So there are several examples we can consider. And let's say that this parameter can have, due to the restrictions that's imposed on the system, n possible values, y1, y2, all the way up to yn, can take n possible values. Okay. And for a specific value of this parameter y equals y sub I, the ith value of this parameter, corresponds to a certain number of accessible states, omega I accessible states. So let's say that, for example, first accessible state, second accessible state, and third accessible state all satisfy y is equal to y1. And 4, 5, 6, 7 satisfies y is equal to y2, etc. So for each discrete value of y, I have a corresponding number of accessible states that gives me that value of y. Then I ask myself, what is P sub I? That is defined as the probability of y, parameter y, having a value y sub I. Well, for each accessible state, I have the same probability, right? I have the postulate of equal a priori probabilities. So that means I have omega I accessible states corresponding to this y sub I. So I'm counting the probability of all of those accessible states. For the first one, I have 1 over omega. Second one, 1 over omega. Or third one, 1 over omega, etc. All the way up to 1 over omega for all of those omega sub I states. So therefore this probability is equal to the number of accessible states that give me this value of the parameter y divided by the total number of accessible states omega. So I have found that what I need to do is to count the number of accessible states of the system and consider the ones that correspond to this a particular value of y, and that the ratio of omega sub I divided by omega will give me the probability of y having a value y sub I. So now that I know the probabilities assigned to each possible values of this parameter y, also I can calculate its mean value, that is by definition go over all possibilities, multiply the probability of having a certain value multiplied by the value. So this is the definition of mean value. So this will give me the mean value of this parameter y is 1 over the number of accessible states of the system, I equals 1 to n, omega sub I, y sub I. So I have to multiply the possible values of y with their corresponding number of accessible states, add them up and divide by the total number of accessible states. And similarly, I can calculate the variance or the dispersion of y. This is by definition the sum from I equals 1 to n, y minus y bar square for each value of y multiplied by the probability p sub I. So therefore, I will find that the variance will be given by delta y square bar is 1 over omega summation from 1 to n y sub I minus y bar squared multiplied by omega I. So I have a recipe to calculate the variance of y as well using this formulation. Now let's talk about two concrete examples. We had this situation, ideal spin system consisting of 4 spin 1/2 particles, each with magnetic moment mu0. The system is placed in an external magnetic field B and isolated. Total energy of the system, since we have discussed this in detail before, I'm just going over what we found previously. If the total energy of the system is minus 2 mu0 B, I can list the accessible states of the system as plus, 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 minus sigma values for each spin, plus, plus, minus, plus, plus, minus, plus, plus, and minus, plus, plus, plus. Remember, sigma is the quantum number. It's equal to plus 1 if the moment is pointing up, minus 1 if the moment is pointing down. At equilibrium, we're going to have for each accessible state the same probability, 1 over omega. The number of accessible states will be equal to 1 over 4. As you can see, I have omega is equal to 4 here. Total 4 accessible states. So what is the probability that the first spin has an up moment? So in order to answer this question, I have to look at these accessible states and find the ones for which the first spin has an up moment. Okay, so first spin sigma 1 is equal to positive, plus 1. So this out of these four cases, there are omega plus number of them, where the first spin has, let's call this omega 1 plus, the first spin is plus, has an up moment. There is three of them, right? So which ones are those? These are plus, 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 minus, plus, plus, minus, plus, and plus, minus, plus, plus. The fourth one is missing. The fourth one has the first moment down. So since omega plus 1 plus is 3 and omega is equal to 4, the probability of having the first moment up, probability for 1 plus, is equal to omega 1 plus divided by omega. So probability of 1 plus is equal to 3 divided by 4. So this will be the answer to part A of this question. And if I look at part B, what is the mean magnetic moment of the first spin? Well, for P1 plus, I have 3 over 4. So you know that the first spin can be up or down, and this probability should add up to 1. It's either up or down. So P1 minus is 1 over 4. And the mean magnetic moment of the first spin, that is mu bar for the first spin, is going to be equal to P1 plus times corresponding magnetic moment plus mu 0 plus P1 minus corresponding magnetic moment minus mu 0. So multiply the values with their corresponding probabilities and add them up. So that's the recipe. So we have 3 over 4 mu 0 minus 1 over 4 mu 0. So the answer is 1 over 2 mu 0 for the first spin mean value of the magnetic moment. Now you can notice here that for the first spin, P1 plus is not equal to P1 minus. The probabilities of the spin being up and down are not the same. And why is that the case? Because first spin is not isolated. It's the system of 4 spins that is isolated. So the probability of being up or down for the first spin are not equal, since the system is placed in an external magnetic field and the total energy is fixed. The total system of 4 spins is isolated, not the first spin. Let's look at a similar situation in example 2. Consider an ideal spin system A with 3 spin 1/2 particles, each with moment mu 0, and another ideal spin system A prime with 2 spin 1/2 particles, each with moment 2 mu 0. The combined system is isolated, has a total energy minus 3 mu 0 B when placed in an external magnetic field B pointing up. Find the probability that system A has a total magnetic moment 3 mu 0 or minus mu 0. So first of all, I have to remember this is again a problem we considered before. In order to have a total energy of minus 3 mu 0 B, what are the accessible states? A star, that is A plus A prime, is isolated and it is at equilibrium with this total energy minus 3 mu 0 B. So I have to count the accessible states. Accessible states we have found in a previous discussion, you can have the all sigma values for the first system, the unprimed system, positive, then you need to have positive, negative, or negative positive sigma values for the primed system, so that you will have a total of 3 mu 0. 3 mu 0 plus 0 mu 0 gives you 3 mu 0 total magnetic moment. And the second scenario was you can have one of them up, plus minus, minus, and in this scenario you need to have both of them up in the primed system. So this will give you 4 mu 0 in the primed system, and you will have minus mu 0 as the total moment in the unprimed system, giving you plus 3 mu 0. So you can have this scenario, you can have minus plus minus for the unprimed system, plus plus, and then as the fifth possibility you can also have minus minus plus plus plus. So these were the only accessible states, giving you a total of this is 1, 2, 3, 4, 5. Number of accessible states is 5. Okay. Now I have capital M, the total moment of system A, total magnetic moment of the unprimed system A. This can be equal to 3 mu 0 or minus mu 0. There are two possibilities. And for M prime, the total magnetic moment of A prime, I have the corresponding value. It's either 0, so that 0 plus 3 adds up to 3, or 4 mu 0, so that 4 mu 0 minus mu 0 corresponds to 3 mu 0. So these are coupled, right? So they have to be together in order to satisfy this restriction. What is the probability of finding system A with magnetic moment 3 mu 0? Well, probability that M is equal to 3 mu 0 is the number of accessible states where I will have M equals 3 mu 0 divided by the total number of accessible states. So which states give me M is equal to 3 mu 0 and M prime is equal to 0. So you can find that these are R equals 1 and R equals 2. So these two states. So I have a total of 2 divided by 5. Then what is the probability that's also equal to the probability that M prime is equal to 0, right? So these two are coupled. So that's also answering part B of the question at the same time. And probability of having M is equal to minus mu 0, which is equal to the probability of having M prime is equal to 4 mu 0. Since I have only two choices for M, this should be 1 minus 2 over 5, 3 over 5. So the first one is 2 over 5, and the second one is 3 over 5. What is the mean value of the total magnetic moment? So that's for part B of the question. Well, what is the mean value? So I can have with a probability M is equal to 3 mu 0 multiplied by 3 mu 0 and plus probability M is equal to minus mu 0 multiplied by minus mu 0. So I have 2 over 5 times 3 mu 0 plus 3 over 5 times minus mu 0. So what will be the answer then? 2 times 3, 6 minus 3. So the answer will be 3 over 5 mu 0. So this will be m bar. What is the mean value of m prime bar? This is basically the first possibility is to have 0 and the corresponding probability is 2 over 5. The second possibility is to have 4 mu 0 and the probability of that is 3 over 5. So this will give me 12 over 5 mu 0 for the average value of the magnetic moment of the primed system. So basically what we learned from these exercises and from this discussion is that it is very important that we count the number of accessible states at equilibrium, and we also need to know the number of accessible states that corresponds to a scenario where we have a particular value of a parameter of the system, because the ratio gives me the probability of that parameter having that value.